I have for you today 20 cones, except they're not really cones. If you look closely, this right here has an octagonal base, and this is not a curved surface. It's triangular. And the key is we have 8 sides here, 16 here, 32 here, and 256. And if you want to see what a 256 sided cone looks like, if you turn on hidden geometry, you can see that these are really just a bunch of lines connected, and these are really a bunch of triangles. So in a way you could say calculus is at work here, because as you increase the number of sides of your cone, you get something that approaches but never quite reaches the actual specification of a cone and a curved surface. So the first thing I did was I cut this cone straight down at the diameter of its circular profile, such that I created a plane that went through the tip of the cone. And that created this right here, which looks like a bow tie, and also like the absolute value functions, if you do something like that. The positive and negative absolute value functions. And I thought this was interesting because what it means in some weird sense is that the positive and negative absolute value functions are a kind of hyperbola. And to the best of my knowledge, a hyperbola is defined as the geometry that you get when you intersect a plane with a cone at this angle. So over here you'll see some more traditional hyperbolas. And you'll notice that they intersect the cone at the same angle as this right here, but just not through the diameter. And you'll also notice on the projection of this hyperbola that you get something that looks like a linear approximation of a curve, and that will straighten itself out as you move from left to right. So what other sort of geometries can you get by intersecting a cone with a two-dimensional plane? Well, circles are kind of a fun one. So if you rotate this cone 90 degrees such that it is horizontal, and then you project that onto a plane, you will get an octagon in the case of the octagonal cone, and you'll get something that looks more and more circular as you add more and more sides to your cone. So once I read a book called Flatland, and in Flatland a sphere passes through a plane, and the inhabitants of Flatland, these two-dimensional creatures, saw something that looked like a point. And this point started to grow in size until it became a small circle. And then it started to grow even more, and even more, and even more. And then it reached the diameter of the sphere, and then it got smaller. Now this cone obviously won't. It will just continue on for infinity meters. But in the case of the sphere, it will obviously taper off and then disappear into nothingness again. And this is sort of interesting because you can imagine that for inhabitants of this reality here, it would be quite odd to see something that seems to break almost all of the laws of sort of what they know to be true about dimensionality. So more on that in a moment. But here we have ellipses, and you'll notice this cone right here is rotated farther through this plane right here than the other 3 cones. And you'll also notice that if I intersect these two geometries with one another and then pull the plane back, the cone that rotated farther through the plane, farther towards 90 degrees like this, created a profile that looks more circular. Now we can see it's sort of egg-shaped, but it's getting there. And over here we have things that are more elliptical. This right here is the result of, again, an octagonal cone, and it's sort of this sort of linear geometry calculuses its way out as we know it to do, but it seems like the top moves a little bit slower than the bottom, which is interesting. And then finally, parabolas. Parabolas and hyperbolas look very similar. The difference is that a parabola will intersect the cone at such an angle that it only generates either a positive or a negative geometry, but not both. So you have a hyperbola creating curvature that is both upwards and downwards, and in the case of a parabola, it will be oriented in such a way that it passes through only one of these cones without ever hitting the other one. Okay, so aside from just being interesting, aside from realizing, well, hey, this is why these are called conic sections and why we learn about them together, what's the practical use of this? Well, we were touching before on the idea of higher dimensions and sort of what higher dimensional objects look like when they are projected into lower dimensions. So we're going to confirm, well, hang on, let me think about how to do this. So let's take a look at the two-dimensional profile of a cone that has actually been graphed and see if we can learn anything about it. And I'll just draw your attention briefly to the fact that the hyperbola and the ellipse here have the same equation, y squared over a minus x squared over b equals 1, except there's a minus sign here and a plus sign here. So if we make this term here negative, this becomes a minus sign, and we're left with a hyperbola. So if you graph these equations in Desmos, you'll notice something fairly interesting when you start playing around with the variables. So if you move a, we can tell this looks like a cone of some unspecified sort of geometry. And we can tell that this is a cone with sort of unspecified dimensions that is just intersecting with, shall we say, a piece of paper. And as you move and modify A, it almost looks like the cone is being pushed towards you as you reduce A, and conversely that it's going farther away from you as you increase A. So that's sort of an interesting visual. And it kind of gives you more data about what this higher dimensional object might look like based on the fact that it's passing through in the way that it is. So this is moving the plane in and out or moving the cone up and down depending on your relative perspective. But what happens if you modify this equation so that this becomes a positive sign? Well, one way to do that would just be to add a positive sign, but you could also make b here negative, and then you would be subtracting a negative and therefore adding a positive. So if we make b negative, we should expect to see an ellipse, and that is exactly what we see. Now, given the context of our cone example, you can almost see how this ellipse just looks like a circle that's been rotated out of our field of reference. And this insight is confirmed if you make b more negative and observe that this ellipse becomes more circular and almost looks like it's rotating towards us until we're staring down the barrel of the circular profile of the cone. So it looks like it's rotating towards us, and then when b hits -4, we have something that looks circular, and then as you rotate b back out, up until it gets to be 0, where it's impossible to see, it continues to become more and more elliptical. So this is personally interesting because while we understand 2 and 3 dimensions well, we don't particularly understand the 4th dimension very well. This, for example, is a 3-dimensional projection of a tesseract rotating through a 3-dimensional plane, just as you would have a cone rotating through a 2-dimensional plane. Mind-bending. But there's another interesting application of this. Human beings often think about ourselves as 3-dimensional creatures. After all, we can move along the x-axis, the y-axis, and the z-axis. But the truth is, we also move through time. And it can be interesting, though we can't really choose a direction for time, you can imagine that in a YouTube video, for example, if you're dragging the slider of the video, you're moving the video through time in a sense. And in that way, you're sort of ascribing a direction to time that you can modify as you move the play button back and forth. So in a similar way, what you can do is imagine for a moment that you're a two-dimensional creature moving around on a plane. You can almost view the z direction as time. And if you do that, and you move a cone through a plane at a constant rate, you'll notice that though time is passing, you're generating a circle that continually grows in size. Well, originally it shrinks in size and then it continues to grow, presumably for infinity with the case of the cone. This is interesting because it gives us an insight into the fact that time is, in some sense, the fourth dimension. And here's another cool visual that I found. This right here is exactly what I'm talking about. You'll notice this is a two-dimensional profile of a human being walking. After all, we have 3 dimensions to work with, and one of them, in the case of this example, is time. And you'll notice, though we can't move backwards in time, this example right here can, and it's treating time just like it's the z direction, and this laser profile right here as the x and y axis. And so that's interesting. It shows you how a lot of things in math that seem unrelated are actually quite connected. That you can go from looking at the two-dimensional projections of a cone and wind up thinking about time or the fourth dimension or dimensions higher than that. You can start by observing one thing about our world and end up at a completely different, new, and perhaps original insight. Thanks for watching.